What would be great is if you just had a list of problems and they just said take the derivative, right? And without even taking the derivative, the idea is, can I identify what rules are inside of it? And so one thing you kind of know you have a chain rule-ish situation when you have parentheses are a great clue for that. So if I looked at this, right, well, the 3 in the base, it's not 3 to the x. If it's 3 to anything more than x, that in itself is a chain rule, right? And then when you looked up in the exponent, you had tangent of stuff that was more than just x. So, well, then there's a second chain rule. So we actually had a double chain rule in this problem because you had the chain rule here, and then when you took the derivative of this, you had to apply the chain rule again. That problem I wrote on the board today, right, where I had, right, a radical of a bunch of stuff, right, divided by some stuff being multiplied by some other stuff, right? So this radical really is all raised to the 1/2. So really the radical you can think of as a set of parentheses, okay? And so that told me if I'm zoomed out, it's a whole bunch of stuff raised to a power. So that in and of itself is a chain rule, right? Then when I try to go inside and look and see what do I take the derivative of this stuff? Well, if I'm still kind of slowly zooming in, right? Well, then the first thing I see is I've got a quotient. And quotient rule only goes into effect or is only necessary when you have x's in the numerator and x's in the denominator, which I have. So there's definitely a quotient rule here. Then I know to do the quotient rule, I have to do the numerator and the denominator. I have to deal with that. So in the numerator, I got a chain rule. I got parentheses raised to a power. That's a chain rule problem, right? In the denominator, I got a product rule. And then when I do each piece of that product rule, I got another chain rule I got to come up with, right? Because I've got more parentheses. So I have no idea what the derivative of this is, but I already know all the steps I'm going to have to do. And, and I may find more. Sometimes you just don't find them all, but I'm like, oh, this is a chain rule with a quotient, and then inside of that quotient is a product rule, and then each piece of that's got a chain rule attached to it, So you can sort of start finding tells in the equation that are going to clue you in. And parentheses are a good key. If you have parentheses nested inside of parentheses, that's another big clue that you've got a chain rule. So like I could write something like this. I could say the square root of the sine, right, of cosine of x squared plus 5. This is a triple chain rule problem. I've got the parentheses on the outside from the square root. Then when I get inside, I got sine of some stuff, so that's another chain rule. Then when you get inside, again, you got cosine of more stuff, so there's another chain rule. And then when you look inside the cosine, you've got more than just x there, okay? And so I'm actually going to show you how to do the derivative of this. It's really easy, and how to nest your chain rules, okay? So let's say this is just a hyper-extended chain rule problem. But let's say we do sine of cosine of x squared minus 5, okay? So I think we're all okay. And by the way, sometimes when we switch in an actual equation, we use different shaped parentheses, like when we go to brackets and things. The only reason we do it, it's not like interval notation where they have meaning. The only reason we do it in problems is so you can see the different sets of parentheses, because if we just use the same ones over and over again, it's hard to see what's inside of what. So on this guy, if I'm breaking this down, I go from the outside in. So the outermost function, sorry, this is not focusing for me. All right, so the outermost function is just u to the 1/2. That's all that's going on there, right? And the u is sine of cosine of x squared plus 5. So you know that you've defined the outer function properly when the derivative is really easy to take. That if you're doing chain rule and that guy's not easy to take the derivative of, you probably haven't defined it right. So this guy is 1/2 u to the negative 1/2. Now to find u prime, I have to do another chain rule. So I'm going to call this g, just to have different names, right? So the outer function here, let's call it sine of v. I'm just going to use a different letter. The inner function is cosine of x squared plus 5. So g prime is just cosine of v. But if I want to find v prime, I got another chain rule. So let's do it again. So I'll call this guy h, and we'll say cosine of w. Just use a new letter, right? Where w is just the stuff inside. So chain rule is like the ultimate procrastination tool. It's like, I don't want to deal with that yet. I don't want to deal with that yet. I don't want to deal with that yet, right? So then here, if I want h prime, well, the derivative of the outside function is sine of w, and the derivative of w, oh, finally I can do that, right? I don't have to keep punning. So now, if I want to build my way back up, well, this times this goes here. So negative 2x sine of w, which was x squared plus 5. Then this times this gets me to there. So I'm going to say, well, negative 2x sine of x squared plus 5 times cosine of v, and v was cosine of x squared plus 5. And now, to get my final derivative, it's this times this. And just for room, I'm going to write it down here because it's going to be pretty long, right? So this is 1/2 u is right here, sine of cosine of x squared plus 5 to the negative 1/2 times u prime. So times negative 2x sine of x squared plus 5 times cosine of cosine. And so all I'm doing, I'm not even really thinking that hard in this problem. All I did was tear it down piece by piece, build it back up, and by the time I was doing this part, I was just copy and pasting. Insert, insert, insert. And so by the time I came down here, I was just literally transcribing the work I'd already done, but I just broke it down into manageable pieces. So this isn't necessary, but it's really helpful when you're learning this. Colors, break it down. You know, I kind of like indent, almost like I'm making an outline in English class or something, you know, and then I just build my way back up to the top. So this is like a triple chain rule. So there are ways to like organize your stuff, but the question is really good though, because you should have a strategy headed into the problem. You may not always guess the right thing, but you should always have some kind of clue of what I need to do. And when you're working problems at home or you're working web work problems, maybe jot down what you think you need to do to solve the problem and then try to do it. You know, and if you get to the right answer, then you know your intuition was right? And so that's kind of what web work's great for, is if you use it of, okay, I'm going to come up with a plan for this problem and then execute that plan, and if that works, you know that plan is solid, right? And next door is where they do the math department study hall, and it's every day, Monday through Thursday, in room 222 from 3:30 to 7:30 p.m. So it's 4 hours, 4 days a week, and then on Fridays it's 3:30 to 5:30. So I can still keep doing this on Mondays, but if you just really want to go in there and work on some problems and have somebody there to like help you out, the one thing you're going to have issues with though, the web work they can help you with, but you know, just be careful about some things about like notation and showing your work. They're not really going to concentrate on that. They're going to concentrate on helping you get the right answer, and that is a primary focus of our class. So if you're ever not sure about your notation, bring that to me in class, or we can talk about that on like the Mondays. But then, you know, if you just need extra help, that's free tutoring. And then Millage Hall, they have tutors available until like I think 9 p.m. is when Millage Hall's open 4 days a week. And then, so, you know, there is some help you can get if you need it.
Okay, so I'm good with the stuff we did today, but you know when you do like the ln and then x plus 5, then derivative of that is 1 over x plus 5. Why do you multiply that by the derivative of the denominator? Like,
Okay.
Is that a rule?
Yes, that is a rule. So what is the derivative of x plus 5?
1.
That's why you only had a 1 in the numerator. So it's u prime over u every time. It's just when you're used to seeing the 1, check the denominator, the derivative was only 1.
What helps me with that is I think derivative over original.
So look at this.
Wait, but then there's another one, and it's 1 over 4x plus 1, and then derivative of the denominator is 4.
Right, but watch this,
Okay.
right? So it's still u prime over u. Your u is x plus 5, so x plus 5 goes in the denominator, but what's the derivative of the denominator? 1. Over here, 4x plus 1 is in the denominator, but what's the derivative of this denominator? 4.
Oh, I just didn't multiply and put it in the numerator.
So it's u prime over u every time. It's just when you don't see anything come up in the numerator, it's because if you check the derivative of the denominator, it was only 1.
Oh, wait, where's it say it's u prime?
I was writing that down in class. So it's the
Okay.
chain rule. So the derivative, the outside function is ln of u. The inside function is x plus 5. So this is 1 over u, and this was just 1. But on this one, u was 4x plus 1, so the derivative was 4. And so if you multiply these two things together, it's really just that. It's 1 over u prime.
Okay.
Mm-hmm.
Oh, okay.
Mm-hmm.